new chapter, which is the Schrödinger equation for hydrogen atom. In the previous chapter, we learned this angular momentum operator, the eigenstates, eigenfunctions, L square and Lz, and also how to construct this spherical harmonics y or n. Today, we will take advantage of such previous knowledge to study the electron opening around this nucleus of a proton, and which is essentially this hydrogen atom. We know that this Coulomb potential V of r is spherically symmetric, right? So it is a function of only the magnitude of the distance, okay, between this electron radius vector r and the nucleus core origin. Okay, so it doesn't depend on any other variables. As a result, this Hamiltonian shows a spherical symmetry. We should take advantage of such a spherical symmetry to express this Schrödinger equations or eigenvalue equations hydrogen atom in spherical coordinates. This p square is the square of the momentum operator, which is proportional to this Laplacian operator, which is the second derivative of the space coordinates x1 and z, a sum over this second derivative of this x and 1 and z. But then you could rewrite this summation of this second order derivative in terms of the spherical variables d by dr, or d squared by dr squared, the derivative of the angular variables, like this. So you could check this basis or coordinate transformations between the Cartesian coordinate and the spherical coordinates easily. Then you could rewrite this p square in terms of the delta square or gradient square, and then gradient square is written in terms of this d by dr and d by d theta and also d by d phi. But if you recognize this angular dependence of this part, this derivative, you will immediately see that this is nothing but L square divided by h bar square, right? Remember that. Okay? And if you go back to this angular momentum operator, the previous chapter, you will immediately recognize that this second order in theta derivative plus cotangent theta d by d theta plus 1 over sine theta squared times d squared by d phi square is precisely the square of the angular momentum operator divided by h bar square. Of course, it's 1 over r square as a prefactor. But what about this d by dr? Well, this is the derivative involving this radius part of the vector, this d by dr. So then you could easily just decompose this gradient square in terms of the derivative involving only the radius vector and plus or minus this angular part. This angular part is given by L squared divided by h bar square r square. So then it is very easy to rewrite this Schrödinger equation for hydrogen atom in spherical coordinates in the following form. So in general, this psi is an eigenfunction of a hydrogen atom, is a function of r theta and phi, but we could decompose this gradient square in terms of derivative involving this d by dr and the remaining angular part, which is L square. But we know what this eigenfunctions of L square. It is nothing but the spherical harmonics, right? So L square has the following eigenstates described by this spherical harmonics y or n. In the previous chapter, we proved this already. Remember, this eigenvalues L square is L times L plus 1 times h bar square. As a result, we know that this y or n is actually decoupled from this spatial derivative like d by dr. It is independent of d by dr. This gives us a very useful hint or educated guess that is the full solution of this Schrödinger equation for hydrogen atom, psi as function of r theta phi, could be written in such a product. This kind of a separation of variables is actually coming from the observation that you have two independent functions. One is a pure function of r, another is a pure function of theta and phi. Of course, this is the 1 over r squared, but this doesn't play a role when you just study the eigenstate of L squared. So we know that this Ym is the eigenstate of L squared. We have another term which involves only the radius part, the r. So we could guess that maybe, it just maybe, the full solution is made of the product of these two functions, and the first one is a function of radius part only. It doesn't involve the theta and phi. The second part is precisely Ym, because we know that this is the eigenstate of L squared. So we are almost there, except we should find out what this capital R as function of r is. Of course, this capital R is a eigenfunctions of this radius part of the Schrödinger equation, which carries these two indices, L, and we know what L is. L is just a quantum number of angular momentum operator, L squared, or Lz. We don't know what this n is, but we will see later that this n stands for the principal quantum number. It is precisely the quantum number in the Bohr radius. In the Bohr theories, that this electron circling around this hydrogen-like atom shows this quantized orbitals or orbits. Remember that in the Bohr theories, we know that this electron circling around this nucleus core, like hydrogen atom or helium atom, with a specific orbits, and these orbits defined by their principal quantum number. The closest orbit to this nuclear core is given by n equals to 1 state. This eigenenergy is proportional to 1 over n squared. Remember that from your general physics 1 or modern physics or introduction to solid, this introduction to quantum mechanics. So you know that this in the Bohr theory, this energy of this hydrogen-like atom shows the, say, a negative energy, which is inversely proportional to n squared, where n stands for this principal quantum number, which labels the orbits. But of course, we know that this is just a semi-classical picture. This picture is wrong if you examine how these electrons are distributed as a probability density around the nucleus core. Because we know that there is no such a thing as a circular orbit in quantum mechanics. So electrons are not just like the classical object, like planet motions, like Earth circling around the sun. No, electrons do not make circular orbits around this nucleus core. This is just a semi-classical picture, but this picture captures some aspect of this quantum mechanics. We will see later in this chapter that this kind of a picture should be replaced by the probability distributions of the electron eigenfunctions, such as this. We will look for these eigenfunctions in hydrogen atom. The square of this psi stands for the probability distributions of that electron will be found in this kind of a location. Okay, so of course this can look like a circular orbit, but in general cases they are not circle at all, and they only represent this distributions in the three-dimensional space. That stands for the probability that we could find such electrons somewhere. This is just an ansatz or starting point, an educated guess that we could try to separate this psi into two parts. One is the wire n, another is the radius part of the eigenfunction. We plug in this kind of a starting point, or our educated guess, back to this Schrödinger equation, and we see whether we can find a solution of capital R. So this angular part is simpler because we already studied the eigenstates of L squared, which is precisely y over m. So we will take advantage of that. Because of that, we will guess that the full solutions of the eigenvalue equation for electron in the hydrogen atom contain the factor of y over m, because this is the eigenstate of L squared. And the Hamiltonian of a hydrogen atom could be written precisely in this form, L squared divided by R squared. Sounds reasonable. I answered your question already. Why should I guess that the solutions take this form? My answer is twofold. One is from this L squared, the eigenvalue equation for L squared. Another is that you have another piece of this equation which is purely R dependent. So that this is, of course, you may wonder why you should guess this. You may have this R plus y over m. Of course, you can try. Okay, if you could find the solutions, be my guest. Or any other combinations of R and y over m are also possibilities. But I think this is the most straightforward and intuitive way to guess this general form of this psi r theta phi. So let's just plug in this answers into the Schrödinger equation for hydrogen atom. It's given by this. So let me make a remark. This capital R shows the dependence of the two quantum numbers, the principal quantum number and the orbital angular momentum quantum number. And in L, why is that? Again, this is something that we assume or we guess. So the reason why this capital R carries this two quantum number indices will become clear later. You may just ignore this dependence. We will derive the dependence of capital R on this principal quantum number, little n, orbital angular momentum quantum number L. Okay, so let me just define this n. You know that. So another remark is that there's no dependence on this little m here, which is the quantum number for the LZ component of the angular momentum operator. And the reason why this is absent will become, again, clear later. Consider a Coulomb interaction with a potential in this form. There's a 1 over r potential with a minus sign, representing that this Coulomb force is actually attractive between electron and the nucleus core. And there's a proton, neutron, electron. A neutron carries no charge, it's a charge neutral, but the proton carries positive charge with the same charge as electron charge. So in the hydrogen atom, the Z stands for the atomic number, which is 1, okay, which means that there is one proton with charge Z, where Z is 1 for hydrogen atom. So let's just plug in all this definition, and we get the differential equation for the radius part of the Schrödinger equation. Okay, so you could move around these equations between the left-hand side and the right-hand side of the equation, and you could simply just move things around. This looks horrible, but we can make progress by the following simplifications and abbreviations. So we could define some dimensionless variables which help us to clean up the notations and simplify these equations. Okay, so we defined two variables. One is called rho, which is the radius, the magnitude of the radius vector, r times some prefactor. And inside the prefactor is the square root of this, the mass, effective mass, mu, of electron times this magnitude of the energy. So remember, the potential, the Coulomb potential in the hydrogen atom is actually negative. value. So if I plot this, so let me plot this right here. If you plot this V of r, you'll find this is negative, showing this minus 1 over r times some prefactor. 0, this is r, the magnitude of the distance. The potential is actually the well. It's a potential well. So from the potential well problem in the previous chapter, you know immediately that you may find a bound state. So this is a very important point. Whether you have a bound state, and how many bound states are there in the hydrogen atom. So remember, the definition of the bound states are the states that are bound by this potential. These particles in the bound state cannot escape from this potential well. We will see that these bound states are simply just the states described by the Bohr theory, roughly speaking. You'll find later that this energies of the bound state of the hydrogen atom are quantized. The quantization of the electron energy in those bound states follow precisely the Bohr theory. But it will be more convenient if we just defined a dimensionless quantity. You see that this dimension for the square root quantity is precisely 1 over distance, which cancels with the dimension of the radius. Distance r in the numerator, so then this rho is actually dimensionless. It carries no dimensions. 没有量纲的，没有单位的。So another quantity called lambda, which is this quantity over here, and we will take advantage of this kind of a definition later, which is given by the z, the charge factor, times this alpha, where alpha is so-called fine constants of atomic physics, which is 1 over 137, which is just a universal constant. Also times this factor right here. Anyway, so you simply just plug in this newly defined variables back to this Schrödinger equation for capital R. You will simplify this equation, and we will take a short break. When we come back, we will simply write down this Schrödinger equation for capital R in terms of this rho and lambda. So this lambda also carry no dimensions. Okay, so you could verify that. 这部分呢比较是计算哈，但是呢我们也可以从这边可以学到不少物理啊。那我们等一下去解这个 Schrödinger 方程式哈，氢原子的 Schrödinger 方程式。那各位会发现说这个镜像哈 radius part of equation 跟简谐正子的那个量子力学的比如说这个本征方程式哈 eigenvalue equation for harmonic oscillator 非常接近，非常像哈。那我们用的数学方法也是非常接近哈。那我们第8章会迅速一点啊，因为所需要的这些工具在前几章都学过了哈，所以我们只是拿来应用到氢原子这上面而已哈。So the dimensionless variables in terms of rho and lambda, the Schrödinger equation for this radius part, capital R, is given by this expression here. Okay, so it looks horrible, but we could again play the same game that we played when we studied harmonic oscillator problem. Remember, when we solved this Schrödinger equation for harmonic oscillator, we solved it in 2 ways. One is the operator method, the elevator thing. Another is to solve this by brute force. This, this hydrogen case, we do not have, as long as the radius part equation is concerned, we do not have such as elevator available for us to take. We need to actually do it by brute force. Again, study several limits of this equation and find the solutions of this. Remember the rho, so let me just remind you what this rho is. Rho is proportional to the distance times this prefactor. Let's look at this limiting case where this rho goes to infinity. Means that the r here, the radius, is actually infinity, which means that we are far away from the nucleus core. Suppose we are really far away, what happens? This is r, and this is v of r. So suppose r is almost infinity, what happens? In the harmonic oscillator problem, we know what happens when r goes to infinity, and we can simplify this Schrödinger equation for harmonic oscillator. Here is the same thing, so we could make some approximations in this limit when rho goes to infinity. When rho goes to infinity, could simply just remove many terms. When rho goes to infinity, 1 over rho, lambda is just a finite number, and 1 over rho compared to the quarter, 1 over 4, is really tiny. You could just ignore this when rho goes to infinity. Of course, 1 over rho squared is even smaller in that limit. So we neglect this. This 2 over rho here is also very small in this limit. Therefore, we could just ignore many terms, almost all the terms. Okay, this term is gone, this term is gone, this term is gone. The remaining part of the equation is really simple, which is the second derivative of the r respect to rho is just equal to 1 over 4 times r. Okay, so this is the simplified eigenvalue equation for capital R, which could be solved. Of course, this could be solved. And the solution of this is really simple. Capital R is given by exponential of minus rho over 2. Okay, so if you plug in this to that equation, you get things satisfied, right? So this is what? The second derivative of this respect to rho is what? Minus 1/2 times minus 1/2 times e to the minus rho over 2, which is a quarter of the same function. Check. So this is really simple. When rho goes to infinity, you get a solution which is exactly exponential minus rho over 2. But of course, when rho is less than infinity, or is just finite radius, and what happens? So this is the place where we implement the trick study harmonic oscillator problem. Remember, we could propose an ansatz or our educated guess in a more general case where rho is any finite number. So in that case, this capital R as function of rho is given by the product of this limiting case solution, another unknown function, which we call this capital G as function of rho. This is the game that we played. Remember that when we study harmonic oscillator problem. So we know the solution in certain limits, but the general solution is given by solution that limit times some unknown function. And this unknown function of rho in the harmonic oscillator problem expressed in terms of the polynomial of rho. Here is the same thing. We should propose that this capital G as function of rho is a polynomial of rho. But before that, let's just plug in this kind of ansatz. So we plug in our educated guess of this type of solution, capital R, back to this exact Schrödinger equation for capital R. We get the following equations. For G, capital G, Okay, so you simply just plug in this product of these two functions and back to this general Schrödinger equation for R. And now you have to solve this equation for capital G. So we need to simplify this equation in certain limits. So we already learned that the solutions approaches the exponential function e to the minus 0/2 when rho goes to infinity. So let's just look at another limit when rho goes to 0. Because capital G as function rho should be the solutions when rho is finite, which includes the case when rho approaches 0, right? We already have this solutions when rho goes to infinity, and so the remaining part of this function should describe this solutions when rho is finite, which means that it includes two situations. One is when rho is 0 or approaching 0. Another is when rho is finite. So let's just simplify this, this differential equation when rho approaches 0. So you'll find that this again could greatly simplify this equation. In this rho goes to 0 limit, you could get rid of another important terms. You keep only the leading terms, the most important terms, which are which terms that you throw away. So I keep the second derivative terms. This term 1 neglected because the leading term here is this 1 over rho square times LL plus 1, because when rho goes to 0, this term dominates. We keep this. We neglect this lambda term. So we keep that. But you may wonder why we keep this, but we neglect this term. It is because this term shows another rho dependence in the denominator, which is d by d rho. Okay, so when rho goes 0, I think this is the order of, say, 1 over rho squared, so we should keep this. In the same way, so we should keep the second derivative term, because the rho dependence is quadratic rho square or d rho square appearing in the denominator. Obviously, these three terms, the dominating terms, so we forget about the other terms. So let's try to solve this simplified differential equation for capital G, as we already learned from this harmonic oscillator problem. The solution, take this polynomial or some power law of rho. In this case, is the rho to the power of L, so you simply just plug in this solution back to the simplified differential equation, you get satisfied. So let's just do it. So take the second derivative of this G with respect to rho, you get what? L times L minus 1, and rho L minus 2, and plus 2 over rho times L times rho to the power of L minus 1, and minus what? Rho square L plus 1 rho power of L. So you just sum of these three terms, and you get exactly cancelled. And therefore, when rho goes 0, this capital G takes the simple form of rho to the power of L as a solution. We do need that because now we have this limiting, two solutions in these two extreme limits. One is when rho goes to infinity, another is when rho goes 0. Okay, so we could just play the same game that we did for harmonic oscillator problem, right? So for the general solution with capital G, the function rho is what is given by this product of the rho to the power of L times some unknown function, which we call this h function. And this h function is a polynomial of rho in general, so which is unknown for now, but we need to solve this h function. Remember, there's the H function when we solve this harmonic oscillator problem. Remember that. There, we use exactly the same argument. Try to solve this Schrödinger equation for harmonic oscillator in two extreme limits when rho goes to 0 and when rho goes to infinity. In a more general parameter regime, we should propose that this general solutions should have a factor, this polynomial multiplied by this rho of L. So we could plug in this, our educated guess or our proposal back to this Schrödinger equation for capital G, and we look for the equation for this capital H polynomial. Let's write down this differential equation for capital H. Again, this is horrible. This is very messy, complicated differential equation. What's the solution? Of course, we don't know the solution in advance, so we need, again, make some proposal. Suppose that this is just a polynomial with infinite number of terms as function of rho. So I guess time is up, so we could stop here for today, and on Wednesday we will finish solving for this H polynomial for the hydrogen case. Okay, so again, so you could see the signatures of these techniques or this mathematical games or tricks that we played earlier. All the things that we studied previously can be used here. So that's call it a day. We continue finishing this complicated polynomial on Wednesday. So we could combine everything and we study these eigenfunctions of the hydrogen atom. We quantize the energies of this system. And we compare our results to this Bohr theory via a semi-classical approach. I'll see you on Wednesday.